So let me start today by reminding you where we left off. Which was one of the results of EMA and Weems I mentioned. That if you have a projective morphism, pi, from y to x, with both y and x being Gorenstein, and normal, and if you have a tilting bundle on y, then the endomorphism ring of that tilting bundle is Cohen-Macaulay, maximal Cohen-Macaulay always, if and only if pi is this funny word crepant. So what I want to do for the first part of today is say more about this word and try to come at it from a slightly different direction that maybe will be, this theorem perhaps is a great justification for its use, but maybe a more intuitive one. So let's see, let's have another recall. So this is recall prime, that we said an R algebra lambda is, or was, symmetric and for this we wanted R to be a Cohen-Macaulay ring with canonical module. Sorry, let me say Gorenstein instead of symmetric. Let's do it in that order. With canonical module omega, if this co-induced module is projective over lambda. And in the case where we really felt like we understood it, where R is Gorenstein, this is where we get the symmetric that I mistakenly began with. Where symmetric means this amounts to, I guess, is, let me put it in quotes so you can't hold me to it. It's not equivalent, it's a little weaker, but symmetric is the thing I want to focus on, which is that Hom over R, lambda R, is isomorphic to lambda as bimodule. It's the bimodule part that makes it a little stronger. So let's try to, in the interest of getting at this word crepant, let's think what this means geometrically. So let's now let X be a, let's say, just an algebraic variety, normal algebraic variety. And let's talk about its canonical sheaf. omega x. I'm going to use the same notation for this as for canonical modules. And let's suppose that we have a resolution of singularities. Call it, say, pi from x twiddle to x. Then of course, x tittle has a canonical sheaf too. And without going into what these things actually are, one of the basic properties of these is that omega x twiddle is isomorphic to the sheaf Hom over x ox tittle omega x. So now let's assume that we're in the nicest of all possible situations. Let's stop talking about these omega things that we don't understand at all, but let's just restrict to the case where the canonical sheaf is trivial. It's just the structure sheaf. Then is that what I want to say? Yeah. Then the above says, of course, that omega x twiddle is just sheaf Hom of O of x tittle into O of x. There probably are some lower stars and upper stars here that I am ignoring. I'm going to be a little sloppy with. But now if we now impose this condition, this symmetric condition. So if we assume this symmetry condition, what do we get? We get then that the canonical sheaf upstairs is Hom over x, O of x twiddle, O of x. And that's also supposed to be O of x twiddle by the symmetry condition. So, at which, let me put in one more line. This is also pi upper star OX, or if you like, pi upper star of omega x. And this you'll recognize, perhaps, given your photographic recall of every single lecture for the last 5 days, that this exactly the equality or the isomorphism of the far left and the far right is exactly what we called crescent. So this, if you liked to go back to Monday's lecture, if you don't like thinking about maximal Cohen-Macaulay modules, the symmetry condition is related to the crescent in non-commutative crescent resolution. That's a controversial opinion for reasons I don't understand. So how far does this go? I mean, I warned you that I was being a little sloppy, and I got lots of assumptions in place, some of which I'm stating and some of which I'm not. So how far does this connection between this symmetric algebra and this crepency condition go? Well, so here's one thing. There's a fact, which is that a complex Gorenstein normal variety X has a crepant resolution of singularities. Without the word non-commutative there, so I mean really this condition on the canonical sheaves, then X has at most rational singularities. So this is something I alluded to last time, that crepant resolutions it's a very strong condition. They're quite rare in higher dimensions. Concretely, you're only qualified to have one if you have rational singularities. And in fact, Lutz mentioned this Fano condition, but we won't talk about that today. So the question then from this, and this is not hard, this is not a deep theorem, this is a vanishing theorem, Grauert-Riemenschneider, which could be thought of as hard, I guess. So the question then is, if R, with whatever assumptions you feel are necessary, has a non-commutative crepant resolution, must it, or its spectrum, have rational singularities? And the answer is yes. This is a theorem due to Toby Stafford and Michel Vandenberg from who knows, 09 or something like that. Sorry. Which, let me give a slightly technical version of the statement and then what it means for us. So let's let K be an algebraically closed field of characteristic 0, and let delta be a prime affine K algebra which is finitely generated over its center, which I call Z. If this delta is a non-singular Z order, then Z has only rational singularities. In particular, this is the statement I really want. if a, and again, let me go back to the Gorenstein normal case. A Gorenstein normal domain R has a non-commutative Crepant resolution, then R has rational singularities. So this, I don't know about you, makes me feel a little better, a little more confident in throwing the word Crepant around like I know what it means. Let me now talk a little bit about things I'm unqualified to discuss, which is okay because we're going to put on our historian hats and just read the papers. Just a bit of a historical digression, which was explicitly, this context was explicitly mentioned in Will's talk and has been implicit in a couple of others. So what I want to say here is that the original definition of Michel Vandenberg was partly, at least, inspired by the minimal model program. And a conjecture of Bundall and Orlov and its proof in dimension 3 by Bridgeland. So let me say just a few words about this. I won't talk about what the minimal model program is other than it's a program to find minimal models. But it was proposed by Bundall and Orlov that this program, this minimal model program, that there are moves. It's a game in which there are moves. And the proposal was that each move should be thought of as a move on derived categories rather than on whatever you're minimally modeling. In particular, they noticed that blowing up induces a semi-orthogonal decomposition of derived categories. And so what they specifically proposed was, if you consider one of the moves in the minimal model program, a flop, they proposed a statement about derived categories coming from flops. So let me explain what that is. So that is replacing a smooth variety y by y prime, where you have a diagram of this form. I guess I need names for these things. Let's call them F and F prime. Diagram is a diagram of varieties in which F and F prime are both Crepant resolutions of singularities. of X. And other technical conditions that I'm going to ignore. There's more, but that's what I want to focus on. And so the conjecture of Bondol and Orlov is, in this case, that if y and y prime are related by a flop, in that sense over there, then they are derived equivalent. They're bounded derived categories. Are equivalent. And as I say, this is theorem of Bridgeland in 2002. This is okay in dimension 3. And as I understand it, Michel Vandenberg's original motivation was working through Bridgeland's proof and observing some family resemblances with the Mackay correspondence to look for a proof of this conjecture, at least in this case, using non-commutative rings. And so what he proved was the following. Let's let R be a, once again, Gorenstein normal C algebra. X, its spectrum, and pi from x twiddle to x, a crepant resolution of singularities. So we're assuming that it exists. And assume pi has at most one-dimensional fibers, which, for example, is true if you're in dimension 3. Then R has a non-commutative crepant resolution of singularities. Let's call it lambda again. An endomorphism of an R module M. And furthermore, lambda is derived equivalent to x twiddle. So this last line, this is the phenomenon that we observed on Wednesday in talking about quotient singularities of finite groups, that the non-commutative crepant resolution deserved to be called a resolution because it was derived to a real one, complex one, whatever. And then the conjecture of Bondol and Orlov reduces to showing that any two of these things are derived equivalent, which Vandenberg then does. and then with a certain additional assumption that I think I'll skip, obtains the conjecture of von Dahlen-Orlov. But this raises another conjecture, which maybe you want to call the non-commutative von Dahlen-Orlov, raised first by Vandenberg and then also by Iema and Weems, which is a very strong version which would be that all Krepint resolutions of a Gorenstein normal variety, say, the commutative ones and the non-commutative ones are derived equivalent. And this is, again, this is known again by work of Iema and Weems. In dimension at most 3, and they give a very tempting, very concrete, sufficient condition, purely in terms of module theory, which would establish at least that the non-commutative ones are all derived equivalent. The last part of my talk today, I want to talk about something implicit coming from this theorem of Vandenberg, which is the following question: is existence of these non-commutative Krepint resolutions equivalent to existence of Krepint ones? So let me say CCRs, meaning the commutative Krepint resolutions. It's let me tell you what's known. It's known in dimension 3 under, and this is what I sort of tried to shovel under the rug earlier, under some assumptions, which let me just say the word terminal and move on. This is due to Vandenberg. That same 2004 paper. But open in dimension 3 in general, as far as I know. In higher dimensions, dimension 4 or more, as the wise man said, you want it to be one way, but it's the other. And this is known to be false, both directions. In dimension 4, so let me probably finish today with a couple of examples. I'm going to let you go early. Lucky you. So the first example, let's let R be, make sure I get it right, power series in X and Y and Z and T and take the ring of invariants under the Z2 action, the cyclic group of order 2 action, where C2 acts by negating everything. Then we saw on Wednesday that R has a non-commutative Krepin resolution. It's very easy to write down. It's the endomorphism ring over R of the big power series ring. I guess on Wednesday I probably used polynomials, but I was secretly localizing the whole time, and completing doesn't change anything. So this is fine. But R is known not to have any Krepin resolution of singularities. I learned this from a paper of Reed. Perhaps it's more widely known. And this, again, is what I was thinking of on Wednesday when I said that Krepin resolutions are hard to come by in higher dimensions. I can't. I'm sorry, who asked? Oh, yeah, sorry. I can't. Reed does. But I will point out that this thing is not Gorenstein. And this is one of the examples I have in the back of my head tickling at my cerebellum when I'm trying to decide what the right definition of a non-commutative Krepin resolution should be for non-Gorenstein rings. Because maybe this shouldn't have one, and it does maybe by accident. Maybe the definition should be stronger. And finally, yes? Is it? Am I wrong? Oh, of course it does. Of course it does. You're right. I'm sorry. I was thinking 3 variables. Scratch that last paragraph. My mistake. 5 variables the same, though. So replace everything I said but with 5 variables. And finally, just on the off chance there's a home audience on the stream, Hailong Dao gives counterexamples for the other direction. And they are hypersurfaces with commutative resolutions, commutative Krepin resolutions, but no non-commutative ones. For example, something like C power series in x1 up to x5 and kill x1 to the 5th plus the sums of the 4th powers of the others. Yeah, good. The reason that these have no non-commutative Krepin resolutions, and this will be the last thing I say, he shows using a property called Tor rigidity which I won't explain, that a hypersurface with isolated singularity has no non-commutative equivalent resolutions if its dimension is even and at least 4. It's also known for, I think this is a theorem of Chen, though I didn't write it down. For diagonal hypersurfaces like this one, there are explicit conditions, numerical conditions on the exponents that tell you when it has a commutative Krepin resolution or not. So this is just the first one you write down. And that's really all I wanted to say. I appreciate you listening.
Do you ever propose definition? I mean, you're saying that perhaps balancing and strong.
Okay, so now it's not part of the actual talk, so now I can say things that are probably false. I had a proposal, a suggestion that maybe instead of a stronger version for Cohen-Macaulay rings than just being maximum Cohen-Macaulay would be to be totally reflexive. That you ask that this endomorphism ring have finite global dimension and be totally reflexive. This means it's reflexive as an R module, but also all of its X's into R vanish in positive degrees. My student Josh, I think, probably proved on the train up here that forces the base ring to be Gorenstein, but I haven't checked all the details yet. So that's probably too strong. Josh Stengel. I'll plug him. Just on the off chance he's watching. So that was the one I was thinking might be reasonable. Now I have to go looking for more.
Other questions? Okay, let's thank you again, and then we'll resume at 11:30.